Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's lecture, we focus on the effect of the acceleration of piston on the velocity and pressure in the suction and delivery pipe. When the piston accelerates or decelerates inside the cylinder, how it is going to affect the velocity of flow in the pipe, suction pipe, and pressure in the suction pipe. Same in the delivery pipe. First, kindly note that during the reciprocating motion of the piston won't move with a uniform velocity. The piston won't move with uniform velocity. The piston accelerates in the first half of suction stroke and decelerates in the second half of suction stroke. And same is the case in delivery stroke also. So, first point is the piston is not moving with uniform velocity inside the cylinder. It accelerates during the first half of suction stroke and decelerates in the second half of the suction stroke. When the piston is accelerating, the liquid which is in contact with the piston also accelerates. When the liquid in the cylinder is accelerating, automatically the liquid in the suction pipe gets accelerated. Similarly, during second half, when the piston decelerates, the liquid also decelerates in the cylinder. Same, again, it reflects in the pipe also. During the delivery stroke also, if you take, same will be repeated. Then, whatever this acceleration of the piston inside the cylinder or deceleration of the piston inside the cylinder, this affects the velocity in the suction pipe and delivery pipe. That's what just now we saw. So finally, what I conclude there, the velocity of flow in suction pipe or delivery pipe is not uniform. The velocity of flow in suction pipe or delivery pipe is not uniform. It varies. So when the velocity is varying, automatically there is some acceleration in the suction pipe, delivery pipe. And this acceleration is responsible for bringing another force into picture, which we call it as the inertia force. And this inertia force gives rise to the inertia pressure. And this inertia pressure head is which we really did not touch upon previously. So that means the acceleration effect, acceleration of the piston effect is what finally non-uniform velocity in suction pipe and delivery pipe. And this non-uniformity of the velocity leads to development of inertia force, which is equal to mass into acceleration. And once the inertia force is coming, automatically the force is not by area is the pressure. And pressure by gamma will give you pressure head. So that means that Because of the acceleration of the piston inside the cylinder, there is an additional pressure head. There is an additional inertia pressure head that is developed in suction pipe and delivery pipe. And this inertia pressure head depends on the crank position, whether the crank is at 0 degrees, 90 degrees, 180 degrees, how much during each stroke. That is what our study today, and we have to derive what is the equation for that inertia pressure head. So let us straight away go into the derivation part of it. Effect of acceleration of piston on velocity and pressure in suction pipe and delivery pipe. This is our topic today. Already I mentioned during the reciprocating motion of the piston, during the reciprocating motion of the piston, the piston will not move with constant velocity, with uniform velocity. It accelerates during first half of suction stroke and decelerates in the second half of suction stroke, and repeat during delivery stroke. Right? These acceleration, the acceleration of the piston as the piston accelerates, the liquid in contact with piston also accelerates. Therefore, water, the liquid in suction pipe also accelerates. Conclusion is because of acceleration of piston, the velocity in suction pipe is not uniform. Not uniform. velocity changes with crank position. These variations of velocity in suction pipe and delivery pipe gives rise to inertia pressure, which causes variation in pressure in suction pipe and delivery. So now the question is how to calculate the inertia pressure. Let A is equal to area of cylinder. Let us start with that, right? Small a is equal to area of pipe. I take A. The moment I deal with suction pipe, I call it as AS. The moment I deal with the delivery pipe, I call it as AD. Then L is equal to length of pipe. Then in that case, LS, I call it as length of suction pipe. LD, I call it as length of delivery pipe. R is equal to radius of the crank. Omega is equal to the angular speed of crank. And omega is equal to, if you want actually, the theta is equal to the angle made by the crank. Made by the crank. And theta is equal to omega t, where t is the time in seconds. Now let me draw the figure and before taking it up. So this is the cylinder of the reciprocating pump. This is suction pipe. Right? This is the sump, suction valve, delivery valve. I put the piston at one position. This is the piston rod. Right? Then actually, right? This is only dotted line you should show. This is circle. So if I take it, this is called as inner dead center. This is called as outer dead center. Right? Now the crank position is, this is how the crank is. And connecting this to this is the connecting rod. So this is the connecting rod. This is the crank. And this crank is making theta. And this is how it is rotating. Here theta is equal to 0 degrees. Here theta is equal to 180 degrees. This is how it goes. Theta is equal to 90 degrees. Again, theta is equal to 270 degrees here. This is the way it goes. Right? Now, if I take it, listen carefully. At the beginning, the piston is at this position. When the piston is at this position, the crank position coincides with the inner dead center. Now, as the crank starts rotating, next, if I take it, it moves to this distance. The displacement is this. This is how the crank position. How much distance it has moved, an x distance. The displacement of the piston is how much? X. So in time t, you can write in time t seconds, the piston, not piston actually, the crank rotates by an angle theta. Right? The piston moves by a distance. Right? Already I mentioned radius of the crank is r, and this length is equal to length of cylinder, length of stroke, and if I take it, this is r, this is r. So naturally this total, if I take it, it is 2r, and this 2r is equal to length of the stroke. Now next thing is the angle made by the crank theta is equal to angle made by crank theta is equal to, in time t seconds, is equal to omega into t. Omega into t basically. Now you see the figure actually. Here this is, that means if I draw a vertical line here, so this distance, whatever you are seeing, by the time the crank makes an angle, basically the piston moves by a distance of x. Right? Then if I see what is this x is equal to, if you see x is equal to r minus r cos theta. You can see the figure actually, right? So this is total is r. This part is from here to here, it is r cos theta. So r minus r cos theta. Then velocity of piston is equal to, that is capital V is equal to dx by dt. It is equal to d by dt of r minus r cos theta, means omega t. So therefore it is nothing but this will go off 0, right? This is minus r sin omega t into cos omega t is minus. So minus minus will become plus. So it is r, right? Cos omega t to sin omega t into omega. So it is omega r sin omega t. Then what is the acceleration of piston? Is equal to dv by dt. So if you do that same thing, what will happen? It is r omega square into cos omega t, because sin omega t, cos omega t into omega. Already r omega is there. Multiply it then. So this is the next. So we got for the velocity of the piston, acceleration of the piston, two equations we got it. So where we started? We started with the x basically first thing. right? This is the where we start. And this is what is the relation between theta and omega is this. So if I call this as 1, this as 2, this as 3, 4. So acceleration of the piston, I got it. Now what I do from the continuity equation, the volume of liquid flowing per second in the suction pipe is equal to the volume of liquid per second in cylinder. Whatever the volume that comes out from the suction pipe has to occupy the cylinder. So how I will get volume of liquid per second means discharge. How I get actually the discharge? If I see discharge is equal to in the pipe area of the pipe into velocity small v. This is related to suction pipe, which is equal to here basically the area of the piston or cylinder into velocity of flow in the system. So this is area of pipe, this is velocity in pipe, this is area of cylinder, this is velocity in cylinder. Understood? Then let us move. So what we want, already the velocity of the piston in the cylinder I know, but this is what I want because the effect of acceleration on the velocity in suction pipe. So already I know I have calculated velocity of piston. I have calculated acceleration of the piston. This effect, how it changes the velocity in suction pipe and delivery pipe. So small a into small v is equal to capital A into capital V. So small v is equal to, which is called as the velocity in suction pipe, let us call it as, is equal to A by A into V. And what is that? V is equal to, so we already we calculated omega r. Basically, what is that? Just sine omega t. Right? This is, can I call it as 5? So now pipe I got it. When once I got velocity, what is the acceleration in pipe? It may be suction pipe or it may be delivery pipe. You don't need to write suction. Directly velocity in pipe, both same basically, is equal to small a is equal, that is acceleration is equal to d into small v by dt. If I do that, actually how much it will be? A by a into r omega square cos omega t. Then what is the inertia force is equal to mass into acceleration. Mass in the pipe, mass of liquid in pipe per second, acceleration in pipe. Mass of liquid means how I can calculate mass of liquid. So that it means rho into volume. Volume is A into L. Small a into L into acceleration is A by A r omega square cos omega t. Call it as 7. Fine. This is mass, this is acceleration. Then pressure is equal to force by area. So it is rho AL, A by A, R omega square cos omega t divided by A. Answer. So what it will be? Rho into L into A by A, R omega square cos omega. Then now pressure head. Pressure head. Pressure head is equal to pressure by gamma. Pressure is how much? Rho L into A by A into R omega square cos omega t by rho G. Rho will cancel. So what is the answer? Finally, pressure head L by G, A by A, R omega square cos omega t. This is the pressure. Pressure head due to acceleration. This is what you should remember. Shall I call this as actually basically force? You can call it as force is over, right? Then pressure you can force is okay. Pressure is 8. Pressure head is 9. Finally, this is 10. Now, basically, if I recollect, so acceleration, pressure head. This is that we call it as HA, right? It depends on it. HA is equal to L by G, A by A, R omega square, cos theta, as theta is equal to omega t. That means HA depends on crank angle. Now take suction pipe. Suction stroke better. Suction stroke relates to suction pipe. So at the beginning, theta is equal to 0 degrees. When theta is equal to 0, in the equation, whatever we have, in that theta 0, if you put cos 0 is equal to 1. So can I write HAS is equal to L by G, LS I will write because suction. A by AS I will write because it is suction pipe into basically R omega square into cos omega t means basically the cos R omega square. This is the first thing. So cos 0 is equal to 1. So this is positive. Then at the middle, theta is equal to 90. When theta is 90, HAS is equal to cos 90. That means it is 0. So 0. Then at the end, theta is equal to 180. That means HAS is equal to, again, cos basically 180 degrees. Cos 180 degrees means minus 1. So minus LS by G, A by AS R omega square. So it is negative. So this is the suction stroke. Now if I take delivery stroke, at the beginning. Theta is equal to 0 degrees. So there actually HAD is equal to, right, LD by G, A by AD into R omega square, because cos 0 is 1. So this is again positive. At the middle, theta is equal to 90 degrees. HAD is equal to 0. And at the end, theta is equal to 180 degrees. So therefore, HAD is equal to minus LD by G, A by AD, R omega square. So we have calculated acceleration pressure head. So the acceleration pressure head during suction stroke, during delivery stroke. On what it depends on? It depends on the crank angle. So depending on crank angle is theta is equal to 0 degrees, 90 degrees, 180 degrees. Naturally, this will change. So at the beginning of the stroke, the acceleration pressure head in suction pipe is plus value. So for the existing suction head, it adds. At the middle, for the existing suction head, it doesn't add because its acceleration effect is 0. At the end of the stroke, acceleration pressure head is negative. That means the final head at the end of the suction stroke is something less than HS. If you take the delivery stroke, at the beginning of the delivery stroke, it is the HD plus something additional due to acceleration pressure head. At the middle of the delivery stroke, again it is HD only. Acceleration pressure head is 0. At the end of the stroke, it is something negative. That means it is HD minus something. So this is the final conclusion. What is the effect of acceleration of the piston on the velocity and pressure? So at the beginning, the pressure increases in the suction stroke. At the end, the pressure decreases because of the acceleration effect. And at the delivery stroke, at the beginning it increases, at the end it decreases. So all this is the point. So in the coming classes, we summarize it and represent it. Thank you so much for your patience. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.